Hello viewers, welcome to my channel Chemphilic. I am Dr. Mala Das Sharma, a retired professor of St. Pius 10th Degree and PG College for Women, Hyderabad. Using the platform Chemphilic, I am going to teach different topics of all branches of chemistry by adopting a self-designed, innovative teaching methodology that is teaching chemistry through riddles. For this video number 5, a thermodynamic topic is chosen for discussion. The primary objective of making this series of videos is to generate interest in chemistry among the students by making a student-friendly discussion on the selected topics. Hope students will enjoy. Now let's start our riddle number 5. I am involved in all natural processes. My value in the universe is continuously increasing. Because of me, heat cannot be converted completely into work. Under certain condition, my value is 0. So this is our riddle number 5. Let's see the questions. The primary question is, who am I? The other questions are, second question, why is my value continuously increasing in the universe? Third question, in what way I am involved in incomplete conversion of heat into work? Last question, when does my value becomes 0? Now guess the answer of the primary questions. So primary question was, who am I? The answer is entropy. Now, this riddle is framed to discuss the entropy concept, especially the absolute value of entropy and third law of thermodynamics. The entropy is a thermodynamic function and it is the measure of randomness or disorderness of the system. When the disorderness increases, entropy value of the system also increases. Now look at here. Here we have taken the substance in different state. Solid state, liquid state, gaseous state. In the solid state, intermolecular or interatomic attractions are strong and the particles are arranged orderly in the crystal lattice. That is an ordered arrangement. So, entropy of a substance in the solid state is low or minimum. When the solid is converted to liquid, the intermolecular attraction decreases and molecules get little apart from each other. So, this randomness increases. So, entropy also increases in the liquid state. And when it is converted to gaseous states, molecules are far apart from each other and intermolecular attraction is practically nil, and then that is the most disordered state and the entropy is maximum in the gaseous state. So, physical significance of entropy is the measure of randomness or disorderness. Now, entropy increases in all spontaneous processes and all the natural processes are spontaneous, hence entropy increases in all the natural processes and all the spontaneous processes are irreversible. So, we can draw the conclusion, entropy increases in irreversible processes. All these are the statement of second law of thermodynamics. Now coming to the definition of entropy or the expression of entropy. Now, entropy is defined as the heat absorbed or heat released, that means heat exchange, isothermally means at constant temperature, reversibly divided by the temperature at which this heat absorption or heat release occurs. Why reversibly? because this expression of entropy has been derived from Carnot cycle, where all the 4 steps are reversible. Now, let us see the expression. For an infinitesimally small change in the state of the system, the entropy change or entropy can be written as ds is equal to del Q reversible, that is heat exchanged. Let us consider heat absorbed reversibly divided by temperature at which heat absorption occurs. Now, from first law of thermodynamics, we know that heat absorbed at constant temperature by the gaseous substance is equal to the increase in internal energy plus the pressure volume work done by the gas during expansion. And this U plus PV, this term which is denoted by H, it bears another characteristics property of the system known as the enthalpy. So from first law of thermodynamics, heat absorbed at constant pressure, if we consider only the absorption, goes to increase the enthalpy of the system. So therefore here del Q reversible is equal to dH at constant pressure. Now if you differentiate this equation with respect to temperature at constant pressure, then del Q by del T at constant pressure is equal to del H by del T at constant pressure, and this is equal to Cp, heat capacity at constant pressure. What is Cp? Change of enthalpy with respect to temperature at constant pressure is known as the heat capacity at constant pressure, denoted by Cp. So from this equation, dH is equal to Cp dt. So therefore, coming back to the equation of change in entropy, ds is equal to del Q reversible by T. And then finally we can write it as Cp dt by T, because dH is equal to Cp dt, and which is equal to Cp d ln T, because differentiation of differentiation of ln x is equal to 1 by x. So considering that Cp d ln T, like that we can write it. Now coming to conversion of heat into work. Now, using the suitable mechanical devices known as heat engine, heat can be converted to mechanical work, but complete conversion of heat into mechanical work is not possible. Why it is not possible? Because a part of the heat is converted to mechanical work, while the remaining part goes to increase the random motion of the molecules of the system, that is entropy of the system. So the entropy is the measure of randomness, and the amount of heat not used up in performing the work is proportional to the increase in entropy function. Now coming to the absolute values of entropy. Second law of thermodynamics tells about the entropy. But from second law, we can evaluate only the entropy change. That means when the system goes from one state to another state, what is the entropy change, ds, that we can evaluate. Is it possible to find out the absolute value of entropy of an elementary compound? And the answer lies in third law of thermodynamics. Let's see. So, entropy change ds is equal to Cp dt by T. Now, integrating this equation within the limit, that is entropy at T1 temperature and upper limit entropy at T2 temperature, and answer of this integration will be S, and upper limit minus lower limit, that is entropy at T2 temperature minus entropy at T1 temperature, and that will be equal to integration of this right hand side part, that is Cp dt by T within the limit T1 temperature to T2 temperature. Now, entropy of this substance is at T2 temperature can be evaluated by solving this right hand side integration and also by knowing the value of entropy at T1 temperature. This problem is solved by assigning the zero value of the entropy of the solid substance at absolute zero temperature. So once again, if you integrate ds from entropy 0 to entropy St at temperature T, okay, that answer will be entropy at T temperature minus entropy at absolute 0. Entropy at absolute 0 will be 0. So final answer entropy at T temperature, and that will be is equal to integration of 0 to T Cp dt by T. Now this entropy of the solid substance at this temperature T, that is the absolute entropy of the crystalline solid at temperature T. Now, the third law of thermodynamics states that entropy of all pure crystalline solids may be taken as zero at absolute zero temperature. Okay. So, we can determine the absolute value of entropy of the solid. Is it possible to determine the absolute value of entropy in the liquid and the gaseous state? Yes, that is possible. Here is the flow chart. Now, you take the solid state of the substance at absolute temperature 0. Now, suppose it is converted to the solid state at temperature Tf. Tf is the fusion temperature at which the solid is converted to liquid. Now, what will be the entropy change? This delta S1, we are denoting it by delta S1, that will be equal to integration of absolute 0 temperature to Tf temperature, Cp of solid dln This expression already I explained earlier. So, it will go to the solid at Tf temperature, that is fusion temperature. Now, from this solid at fusion temperature, it will be converted to the liquid state, that is liquid at Tf temperature, and this is the phase transition. Entropy change in the phase transition, any phase transition is equal to the change in the enthalpy divided by temperature at which the phase transition occurs. So, this delta S2 is the entropy change during the phase transition from solid to liquid, and that will be equal to enthalpy of fusion divided by Tf, that is the temperature of fusion or fusion temperature. So, liquid has come to Tf temperature. Okay. Now, from liquid at Tf temperature, you can take it to the liquid at any other temperature. Say, here we are taking at T is equal to Tb. That means boiling point of the liquid. So, what will be the entropy change? Delta S3 will be equal to integration of from Tf to Tb, boiling temperature, Cp of liquid state, d ln T. You can take any other temperature also, say T temperature, then it will be Tf to T, Cp, d ln T. So, then the absolute entropy of the liquid at any temperature, say T, that will be equal to delta S1 plus delta S2 plus delta S3. Now, from the liquid, when it is converted to gas, then during this phase transition, entropy change will be enthalpy of vaporization divided by the boiling temperature. Okay, so from this equation, you can calculate the entropy change during this phase transition. So now the gas has come to the temperature of boiling point, that is the boiling temperature. Now from this temperature, you can take the gas to any other temperature, say gas at temperature T. What will be the entropy change? Integration within the limit Tb to another temperature T, Cp of gas d ln T, that is denoted by SF. So what is the absolute value of the entropy of gas at T temperature, that will be equal to delta S1 plus delta S2 plus delta S3 plus delta S4 plus delta S5. Now coming to the answers of the remaining question. Second question was, why is my value continuously increasing in the universe? The answer is, in all spontaneous processes, entropy increases. So, natural processes are all spontaneous, so entropy of the universe continuously increasing. Third question, in what way I am involved in incomplete conversion of heat into work? If part of the heat is converted to work, the remaining part increases the randomness, that is entropy of the system. Now the last question, when does my value become zero? The entropy of a pure and perfectly crystalline substance is zero at absolute zero temperature. So this was our riddle number 5, and I sincerely appreciate your comments and suggestions.